Again, so now we are going to with the decision boundary. So the weight vector is relevant to the decision boundary. The weight vector points in that direction of the vector which should produce an output of that one. So already we discussed this parameter. Vector with that positive output are on the right side of the decision boundary, and if W is pointed in the opposite direction, the dot products of all input vectors would have that opposite sign. So obviously, so that would result in the same classification but with that opposite labels. So the bias determines the position of that boundary. So that is W T, that should be multiplied plus B plus bias, that is the B equal to 0, using one point on the decision boundary to find B. So now we have to see about the decision boundary in two dimensions. So we have to be visualize how that neural network is doing. So it's making forming the decision boundaries. So I'm having that value of that theta, and it's having that weights of I'm having that is that input 1 and then input 2, and I'm having that is the weights W1 and then so W2. It has to be produced, that is one outcome is called that is the theta, and we can able to write that is the boundary equation like this: the output equal to the step of the multiplication of xi in and wi. The same format here we have to be multiply with the w1 in 1 plus W2 multiplied with that into, and we have to be go with that minus theta. So it's specifying that a decision boundary. So the decision boundary between out 0 and out 1 is lies on W1 in 1 plus W2 into minus theta, that should be the 0. So therefore in two dimensions the decision boundaries are always as a straight line, because we are deriving the equation as that 0. So the decision boundary for and or operators, we know how that and is working. So if the both the inputs are 1 and that output of that and is also the same, with that logically we have to be add up that normal 0 1 1 0 and 0 0 1 1. Instead we here we have to be add up that plus 1 plus 1 minus 1 plus 1 minus 1 minus 1 and minus 1 plus 1. So this way we have to be make that decision boundary for that AND operation. So now so W1 equal to 1 and W2 equal to is also 1, and now the theta value that has been that 1.5. So that has been derived from that graph. So we have to change that weights according to that threshold also. So now W1 in that OR operation, so W1 is that 1, W2 is at 1, and the value of that Q is seems to be that 0.5. So now we have to be continually see the decision boundaries for that XOR. So in that XOR already we know if that number of the ones is even, and we have to be extract that output as positive, and if the number of ones is presented in the series is OR, the outcome of that XOR gate is that negative. So we need the two straight lines to separate that different outputs and so decisions. So we are having that either the change in the transfer function, so it has more than one decision boundary, use a more complex network, so that is able to generate more complex decision boundaries. So and now we have to be go with that decision hyperplanes and linear the separability. So if user has two inputs, then the weights define a decision boundary, that is a one-dimensional straight line in the two-dimensional input space of the possible input values. So if we have that n inputs, the way to define a decision boundary, that is in an n minus 1 dimensional hyperplane in the n dimensional input space. So W1 in 1 plus W2 into plus Wn in n minus theta equal to 0. So already we saw in that previous cases. So this kind of that hyperplane is called that linear, or that straight, or it is that non-curved, or it is the flat, and can only divide the space into the two regions, that's in positive side and then the negative sides. So still we have to go with that little more complex is called, that is that XOR type of that problems. So with an input patterns we can classify using the single hyperplane and said to be linear separable. So problems like XOR which cannot be classified as like of linearly separable, so and that should be that non-linearly separable. So with the continuation we are going to see about general decision boundaries.